Hello everyone. Now we will large equation scare you. Well, good news, this isn't even relevant. Okay, so we will be talking now about non-parametric tests. So do you know why these are called parametric? It's because you give parameters to them. Yeah, that's literally it. Do you know the parameters like standard deviation, the data, the mean, the alpha? Yeah, all that. Now, on the other side, this is the non-parametric, the giga-chad chi-square test, which doesn't need parameters. I mean, it needs some parameters, but not as many parameters as the other thing. So the parametric tests, the reason they take parameters is because they're kind of like continuous, like they're on a normal distribution. They're basically, you can just say they're a test, while the non-parametric tests are like a statement. A very common use case for non-parametric test is you have a dice and you roll it and you want to see if is it fair or not fair. That's it. Or if you have people with like blue eyes, with blonde hair, brown eyes, with blonde hair, blue eyes, with black hair, stuff like that, and you want to see if the eyes are eyes related to hair or not. Stuff like that is why you need guys with white skills. Yeah, stuff it's basically like either or. It's a statement. That's when you use non-parametric tests. And the chi-square test is the only non-parametric test we'll be covering in applied statistics. So the chi-square test has the function, well, it has two functions. The first one is G2 GOF, and the other one is contingency table. So this stands for chi-squared goodness of fit test, and this stands for chi-squared contingency table. So goodness of fit, both of them, uh, for both of them to find the critical value, you have used G2 inverse. That's it. These are the three functions you need for the chi-square test. Now I'll give you an example of the goodness of fit test. So here is a normal distribution. You throw a dice however many times. What is the probability of you getting either side of a dice, like 1, 2, 3, 4, 5, 6? Well, actually, before that, what is the chi-square test used for? Goodness of fit. So you have a theoretical output. Well, I'll erase this part of the board. I don't know. I don't remember what n choose k is. I actually think I'll have to study that for discrete in like 2 days, but whatever. You have a theoretical, like a dice. You have a dice and you roll it. Each side has a probability of 1 out of 6, right? So theoretically, if you roll a dice 100 times, it should come up to like one should come 25 times. Actually, no, it's true. Instead of 100, you roll the dice 120 times. That you roll the dice 120 times. Ideally, each side should come up 20 times, right? 20, 20, 20. So if you calculate the results, well, yeah, 100 is 16.6. That's why I chose 120. It's an easier number, whole number to write. So, however, in reality, when you actually roll a dice, you will find that it's not that cut and dry. Maybe you will get one like 18 times, you will get two like 22 times. You will get 3 like 13 times. You will get 4 like 11 times. You will get 5 like 27 times and 6 like 29 times. All of these add up to 120, but it's not fair. That's when you use the chi to goodness of fit test. Like how if he asks in the oral exam, goodness of fit sees how the actual outcome fits the theoretically expected outcome. That's goodness of fit. Also, the real outcome that happens in real life is also called the frequency. You'll see it here. Now we roll the dice 600 times, and you can see that we have to use the goodness of fit if all the sides have the same probability. Actually, no, no, no. Forget about it. It's a chi-square test. So all the sides have 1 by 1 over 6. We roll the sides dice 600 times and we got this result. The possible value of the dice are 1 to 6. Okay. And yeah, that's all you need. You can see here. The possible values of the dice are 1 to 6, which in, MATLAB, this just means vector 1, 2, 3, 4, 5, 6. Frequency is a very commonly used word. Frequency just means the real outcome. When you do it in real life, what do you get? That is the frequency. Expected, they are using repmat, which basically repeats this value 6 times. Well, no, this is the dimensions. They said that they want a 1x6 vector. So 1 row, 6 columns, and they want to repeat 100. I'll show you. You can just literally just write this. You don't need to do all that fancy stuff. Now, this is the important thing. The chi2go function. Chi squared goodness of fit. What are the parameters? Well, the output, there's the H, the P, and the stats. It only has 3 outputs. Stats contains the statistics related to the test. And as for the data, you take die, the expected values, and the frequency, the actual values. And if the confidence is given, then you also have to give the alpha. But for now, you don't. So let's start doing this. Okay, so the frequency, let's write that first. The frequency, the actual output is 83, 91, 122, 107, 74, 123. That will be the frequency. The ideal, which you can also do expected. So the way you do expected is 600 times, right? And each side has a probability of 1 over 6. So you multiply 600 with 1 over 6. So if you do that, 600 into 1 over 6 will give, I think 100. Yeah, 100. Okay. So okay, so the first thing, even before frequency, what you have to do is write the possible values. So just make dice. What are the possible values? 1, 2, 3, 4, 5, 6. You could also just write this, but since I'm demonstrating, I wrote the whole thing. All right, what are the expected values? So in an ideal world, all the sides should have an perfectly equal uh, probability. So it would be 100, 100, 100. And I actually recommend you write it yourself manually 6 times, and I'll show you why. Okay, this is the expected. Now what else? I think that's literally just to help you to go. Uh, Let me just check the notes. Yeah. So here, X is the possible values, and forget edges, is not relevant. Expected is the expected values that we should get, and frequency will be the actual values that we get. So now we do it. And as you know, the outputs that you get from Chi2Go, the chi-square test is H, P, and stats. Stats is just a bunch of statistics related to the test. So then you do Chi2Go. What do you get? What do you put into Chi2Go? The first one is X, which is the possible values. So dice. Then you tell it, okay, expected. What is expected? The expected array. Okay, what is the actual with the frequency? You give it the frequency array, and that's it. That's for the chi. That's the chi-square test. If you run it now, the H is 1, which means the null hypothesis is rejected. And here it does give some other stuff. Okay, the chi2 stat is the result of the chi-square test. DF is degrees of freedom. O is just the frequency, and E is the expected. But right now, just care about this and maybe the degrees of freedom because of critical values. But before we do anything else, I also have to show one more possible distribution. So in this case, this dice, right, each side had equal probability. This is called normal distribution. No, it's called uniform distribution. Now you have one more type of distribution, which I guess it's French, so it's supposed to be pronounced like Poisson or something. But I speak English, so I'm just going to say Poisson. So the Poisson distribution. Poisson distribution is when each possible value has a different probability. It can be more, it can be less. All that matters is all the sides don't have the exact same probability. So I know this looks intimidating, but there's only one difference between doing the Poisson distribution test and the uniform distribution test. Well, you can tell that it's Poisson distribution if they give the probability for each type. So they said what are the values? A can be 0, 1, 2, 3. So let's start from the. Actually, I'll comment out this code so you can just see how little of a difference you have there. So first possible values is your possible values. What are the values? 0, 1, 2, 3, and 4. Here's A0, A1, A2, A3, A4. So there's 5 possible values. All right, so there's 5 possible values. Then the frequency. In real life, what did you get? Well, in this case, let's write the expected first. So before, since each side in a dice had an equal probability, we just divided it by 6. But in this case, each side has a different probability. So we'll see, okay, we took 100 samples for X. Okay, we took 100. So ideally, each side will be, just will multiply their probability with 100. So we took 100 samples. Okay, how many of those are A0? So the probability of A0 is 0.135. So we will just multiply 100 with 0.135. Okay, that's the first value. The second one will be 100 multiplied by 0.27. By the way, these are in the notes as well. And the third value is also 100 multiplied by 270. Fourth is 100 multiplied by 0.180. And the fifth value is 100 multiplied by 0.145. 1, 2, 3, 4, 5. Okay, these are the expected values. That's the only difference from the other one. Then you just do make the frequency, which is the actual values. Just copy them from here. And see. And you do the G2Go test like always. You pass in the possible values, the expected, the frequency, and yeah, that's it. One last thing about the chi-square test. Well, one last thing about this chi-square test is how to find the critical values. So for the critical values, remember how I said you don't need the confidence interval? Amar is asking, this is a special G2 only given if it's a Poisson distribution. No, this is, if you can see here, I use the exact same syntax for the chi-square test if it's a uniform distribution, exact same syntax if it's a Poisson distribution. The only difference is the expected, how we find the expected array. But yeah, how to find the critical value. So you notice how in the results of the G2Gov test, we have the degrees of freedom, or you can even see here 1, 2, 3, 4, 5. That's interesting. I think it's because I haven't run this a dumbass. Yeah, that was the old result. Okay. So here degrees of freedom are 4 because 0, 1, 2, 3, 4, 5. These are 5 values. And as you know, degrees of freedom is -1. So degrees of freedom 4. So to find the critical value in the chi-squared test, we use the function chi2 in inverse. And what are the values given? Well, it takes the confidence interval and the degrees of freedom. So, and this is also in the notes. It says parameters are confidence and degrees of freedom. So, okay, so what is the confidence here? I don't think we are expected to, yeah, I don't think we're expected to find the critical values here. But I'll show you in the, in the actual one. But the parameters are confidence. So if it says, for example, if it says 95% confidence, that would mean you put in 0.95 and the degrees of freedom from here is 4. That would give you the critical values. So with that done, we can now do the non-table chi-square test in the quiz. Okay, this one is the uniform distribution. We're not given a Poisson distribution, but you know how to solve it anyway. So 97% confidence level. We need to check if a dice is fair or not. Each side has the same probability, 1 by 6. We roll it 900 times. So this is important, 97%. Right. So confidence is 97%, which means 0.97. The space is real quick. We roll it 900 times. Let me just write it here. I need 900 times. So I can delete this line. And this is the actual frequency. Pasting it is a pain in the ass right now, but the professor said that he's working on making it easier. So I'll just name it frequency, and I'll put in these values and just fix the formatting real quick. There you go. This is the frequency. What do you mean copy paste it in my tab? Well, either way, it took like, oh, like the website link space. Oh, you mean, oh yeah, actually good idea. It gets rid of formatting that way. Yeah, I'll do that next time. Okay, so this is the frequency. Okay, what else? Actually, no, nothing else. We don't need anything else. Now, we have the frequency. We'll find the expected. So we were given 900, and the probability of getting any side is 1 over 6, right? That means we divide 900 by 6. Mm, So real quick, let me just do it here. 900 divided by 6, because you can always use MATLAB as a calculator. It is 150. So expected is 150, 150, and there's 6 possible values. Okay, that's another thing. The possible values for the dice, 1, 2, 3, 4, 5, 6. 6 possible values. Each one is ideally should come 150 times. There you go. 150, 150, 150. Now you have the possible values, you have the expected values, you have the frequency, and you hmm, does Chitukov need alpha? You don't remember. I think it is recommended to pass alpha. Let's just see what Chitukov expects. Okay, X expected frequency and alpha. Now, one thing with G2Golf here is it doesn't work like it does in MATLAB. So I'll show you what I mean. First, the parameters HP and stats. So in MATLAB, we would give dice. We would give the expected value like this, expected, expected. We would give the frequency like this, frequency. So we would do it like this. But in this case, it's going to be wrong. It says operator 1, the first argument is 1 by 6. 1, 2, 3, 4, 5, 6. The second argument is 1 by 8, which means see this expected 1, 2, 3, 4, 5, 6, 7, 8. So this, it's taking this string as an argument. So what the problem is, it expects only 3 arguments. It doesn't want this marker, so you just have to pass in expected without, declaring it, the frequency, and just give it the alpha. That's all you have to do. Now it works. And another thing is they collapse the stats. Like in MATLAB, you get a lot of stats. Now you only get the G2 stat value, the result of the G2 Golf test. The only other thing that you will need to figure out yourself is degrees of freedom, which you can do like so. 1, 2, 3, 4, 5, 6. Okay, degrees of freedom is 5. Now you will need the degrees of freedom for the critical values. See here, the critical value. So how do you find the critical value? You give it the confidence. So you go here, critical value is equal to G2 inverse. And all you have to do is the confidence, right? Confidence and the degrees of freedom, which is 5. It says the second op was 1x8, which means I shouldn't have given expected as a string like this. I gave it like this before, but I shouldn't have done that. I should have just passed in the stuff, like just pass in the parameters, the dice, the expected, the frequency, and the alpha. Like in MATLAB, you have to do it like this. See? You have to give the possible, you have to first say expected and then give the value of expected. You have to say frequency and then give the value. So yeah, that's the difference. Okay, degrees of freedom. 1, 2, 3, 4, 5, 6. Okay, it's 5. That's it. So you copy the critical value. What is the decision? Decision will be h. H is 1. Which means it's rejected. The value of the test statistic, which will be here, 16.147. And now we just finish the attempt and see if it's correct. Yep, it's all correct. So that is the first part of lab 9. Now what is the second part? The table question. So in the table question, the only thing you have to deal with is to figure out how to represent it in a matrix. So you go here. I'll show it to you in a slide. Here in the slide. Okay, you have a table where you have the eyes and you have the hair, blonde hair, brown hair, black hair. And you have to tell if they are independent or not. So you have to figure out how to represent it as a table. And for this, the method, the function that you use is called G2cont. G2cont. Cont stands for contingency table, just in case the professor asks in the oral exam. So you start making it into a matrix. And this is arguably easier than the other one. Umar, all of these codes are available on the notes. But if you want to see the code, is here. Okay, so this table. In the case of the table, first you represent this data in a matrix. And actually, in this case, it's better if I just straight up start solving the other one because you kind of need the alpha. Right, so let me start a new attempt, finish the view, read and quit. Okay, so I'll show it in MATLAB first. Actually, I don't think MATLAB has G2 cont. Yeah, MATLAB doesn't even have this function, the contingency table one. It's octave only. But what you have to do first is you have to write this data into a matrix. So you create a matrix that goes, okay, so the first row is 26, 26, 22, semicolon, 6, 66, 17, semicolon, 18, 39, 6. So this is the matrix. And what else is needed? 98% confidence level. We need the alpha. So actually we'll need both. So confidence is 0.98. The alpha can be calculated from the confidence. So 1 minus 0. By the way, you can just write it. You know what? For this example, I'm just gonna write it directly. So we have that. Now we can just do the G2 contest, which by the way gives the same output as the G2 Go. So HP and the stats is equal to. It's just that this time we do G2 cont, which takes in two values. The first one is the matrix, and the second one is the alpha, which is 1 minus 0.98. You can either write 1 minus 0.98 or you can just straight up write 0.02. Both work. So once you're done with that, you will also have to find the critical value, which is the exact same way as the previous one. Well, one difference, the degrees of freedom. So you do G2N. The first thing that you provide for the critical values is the confidence interval. So confidence and the degrees of freedom. So in a previous, in the arrays, we just had n minus 1 as the degrees of freedom. However, in matrices, you have this formula, number of rows. No. Yeah, number of rows minus 1 multiplied by number of columns minus 1. It's a very simple formula though. So how many rows do you have? 1, 2, 3. How many columns? 1, 2, 3. So number of rows minus 1 will be 2. Number of columns minus 1 will be 2. Multiply that 4. So the degrees of freedom here will be 4. Boom. And that's all that you need. Yeah. However, since T2con doesn't work on MATLAB, I'm gonna paste it into Octave. H1, the chi-square test result is 40, and the critical value is 11. And yeah, that's it for the table, contingency table G2 square test. This is critical, right? 11. Yeah. So the stat value is 40. H is 1. So the value of the test statistic is 40. That is Cn, which is the H, is 1. And now you finish and test. And it's all correct. So that is the end of the contingency table, or the table questions. Lab 10 will be linear regression, correlation coefficient. uh, and then ANOVA, lab 11. All right, so any questions about this one? I'll give 10 seconds and then I'll close. And I guess the next meeting I'll do it in like 30 minutes because I have to revise a bit of lab 10 as well. Yeah, these are all in the notes. All right, then I'll see you guys in the next one. No, no problem, guys. Good luck in tomorrow's exam. But yeah, see you in the next session. We're not done yet. We still have 10, 11, 2 more labs left. We'll see ya.